So since we have understood why link prediction is a difficult problem, we've also have formally defined what is link prediction. Let us try to understand how to evaluate a link prediction method. Okay. So generally we will not talk about the metric here, we will talk about the evaluation setup. So in case of inferring missing links, right, missing link prediction, not future link prediction. Missing link prediction, what we do, we are given a static network, okay, this one, and what we do, we try to split the edge set E into training set E train and test set E test, okay. So out of say 100 edges, we divide it into two parts. We assume that okay, 80 edges are the training sets and remaining 20 edges from the test set. And so essentially what you need to do, you need to remove these 20 edges from the static graph, right, and your task could be to predict these 20 edges, and these 20 edges are your E test, okay. Now how do you choose these 80-20 samples, right? Now how do you delete, how do you choose these E test samples, right? Of course you can randomly choose edges and delete them, and your algorithm will try to predict those edges. Random deletion is possible. Other possibility would be based on some degree, some notion, either in degree notion or whatever, degree notion or homophily notion, some sort of notion. So why it is important? Think about a network like this, okay, okay, and assume that, okay. So this is a network, and let us say you delete this edge, right, and you want to predict this edge. This edge is very easy to be predicted. This edge is very easy to predict, because these two nodes, this node and this node, these two nodes are part of a cluster, a triangle. So due to the transitivity property, it is highly likely that these two nodes will also be connected, okay. This edge is easy to predict. What about this edge? If I remove this edge, right, then the graph would become like this, okay. So how do we predict that this node and this node will be connected? It is very difficult, because these two nodes are far from each other, okay, and this kind of edges are bridge, right, we discussed in the previous chapters, right. So when we remove a bridge edges kind of connect components which are far apart from each other, and upon deletion of this bridge, sometimes the graph gets disconnected, or the shortest path distance between pairs of nodes increase significantly, okay. So now the question is, how do you choose this E test, right? So oftentimes I have seen people oftentimes cheat, right? So what people do, people selectively choose the remove those edges which are easy to predict, and then show that look, our algorithm produces 90% accuracy, 95% accuracy, and so on. But the difficulty is to predict those edges which actually connect nodes which are far apart from each other otherwise, okay. So how to divide E train and E test, this is important to consider. The second problem, if it is a future link prediction problem, then it is very straightforward. You do not need to delete anything, because you have two snapshots now at Ti and at Tj, right. You have same set of vertices but different set of edges. So given this graph, can we predict this E dash minus E edges, okay. So this is the task. Given this graph, can we predict which edges are going to come to form this network, and this is future link prediction problem, okay. So I have already discussed the issues of positive and negative samples, but let me again reiterate. So when we have V number of nodes, you have mod V C2 number of pairs, okay, and say out of this only you have mod E number of edges which are already there. So mod E number of pairs, mod E number of node pairs are connected, okay. This many number of node pairs are not connected, okay. So your task could be to predict those nodes, those pairs of nodes which are going to be connected in the future. So this, among this many number of pairs, you need to predict how many of them will be connected. And I mentioned in the last lecture that this is really small, say 0.5% of the node pairs will be connected, sometimes 1 or 2, right. So in terms of classification problem, if you think of link prediction problem as a binary classification problem, you have positive samples and negative samples. So what are the positive samples? Positive samples are those node pairs which are already connected through this mod E number of edges, okay, and negative samples are those pairs which are not connected at current timestamp, okay. So you have huge negative samples. It's a massive imbalance classification problem, okay. So how do we deal with this problem? So you can actually do some sort of undersampling. You sample equal number of you basically sample from your negative samples, right, undersample the negative sample population, so that the number of positive edges and number of positive samples and number of negative samples will become equal, okay. That can be one possibility. Other possibility is that, okay, since this is inherently an imbalance classification problem, let's make it imbalance, okay, but not this much of imbalance. Let's make it 1:10 or 1:5, so 1:5 positive is to negative samples, and then we solve it, okay. So since this is a classification problem, as I mentioned, right, the problem here is, not the problem, how do we evaluate a classification problem? If you are familiar with a binary kind of classification problem, we generally draw this confusion matrix. Confusion matrix is a way to understand the false positive, true positive results, right. If you are not familiar with this, I will briefly explain here. So in a confusion matrix, right, binary classification problem, your rows indicate actual predictions and your columns indicate the rows indicate actual labels and columns indicate the predicted labels, okay. Now what do you mean by labels in case of link prediction? So your one instance is a pair of nodes and your label would be either 1 or 0. 1 means this pair of nodes will be connected, 0 means this pair of nodes will not be connected, okay. So this is 1, 0 actual, this is actual and this is predicted 1 or 0, okay. Now look at this cell, say this is 25, okay. It means that there are 25 such instances which are actually positive and your prediction algorithm also says that they are positive. So these are true positive, your algorithm says that this is positive and that is true. So these samples are called true positive, okay. Now let's look at this quartile, okay. So this means, so say there are 10 such instances. So it means there are 10 instances which are predicted as 0, but their actual labels are 1. So so you basically say that it is negative, it is 0, it is negative, but this is false, okay. It is negative, but it is actually positive. So you say that this is negative, but this is false. It's called false negative. Look at this part. Okay. So this cells indicates that your prediction is 1, you predicted it as positive, but your actual level is negative. So this is, so you predicted it as positive, but that's false. So it's called false positive, right? And what is this one? You predicted it as negative and it is actually negative. So this is true negative. You assigned it as negative and it is actually true. Okay. So you may wonder that, okay, you mentioned, so I mentioned this is a true positive, false negative, false positive and true negative, but in this slide it is true positive, this is false positive, right? Why it is so? Because in this matrix, rows indicate predicted outputs and columns indicate actual outputs. But in our case, it is basically the other way around. Rows indicates actual output and columns indicate predicted output. Therefore, this mismatch. Okay. But if you understand the nomenclature, positive, that is true, positive, so this positive, negative, these are with respect to your prediction, and you judge whether it's correct or not based on the ground truth, right? And then you decide whether it's a true prediction or false prediction. Okay. So you have these 4 quantities now. So based on these 4 quantities, one can come up with multiple such metrics to evaluate a system. So first metric is called accuracy. So accuracy is very simple. Accuracy basically says that looks at all correct predictions, and you divide it by the total samples, right? So how many correct predictions are there? True positives are correct predictions and true negatives are also correct predictions. So these diagonal elements are correct predictions. So accuracy is this true positive plus true negative divided by total, true positive, false positive, true negative, false negative, and total basically a TP, FP, TN, FN, if you sum them up, this is basically the number of instances n, right? This is accuracy. Why accuracy is not a good measure, I will discuss later. The other metric is called precision, which is basically saying that out of all the predictions, right, how many of them are positive? Out of all the predictions, how many of them are correct? Out of all the positive predictions, let me put it in this way, out of all the positive predictions, how many of them are correct? So how many positive predictions are there by your model? Number of true positives and number of false positives, because false positive instances are those which have been predicted as positive but they are false. So how many positive samples are predicted? TP and FP, and out of them how many are correct? TP. So this is TP by TP plus FP. This is precision. What is recall? Out of all the positive instances, irrespective of your model's prediction, out of actual positive instances, how many of them have been predicted correctly? How many positive instances are there? True positive plus false negative, because false negative instances are those which have been predicted as negative, but that prediction is wrong, means they are actually positive. So TP plus FN are total number of positive samples, actual positive samples, right? And how many of them are correct? TP. So this is your recall. Precision and recall, numerator is same, but the denominators are different. Okay. Now let's try to understand a bit difficult matrix now. True negative rate, TNR, this is also called specificity. I will use this term later. So true negative rate is basically out of all the links, out of all the samples that are actually negative, how many are predicted by the models to be negative? True negative rate. So how many negative instances are there? Actually, true negative plus false positive. False positive instances are those which have been predicted as positive, but that is false, they are actually negative. So, Tn plus Fp, and out of them how many of them are actually predicted as negative? Tn. This is true negative rate. There is something called false positive rate, okay, or false alarm rate or fallout rate, okay. Remember these terminologies. So, false positive rate is out of all the negative samples, right, how many are wrongly predicted out of all the negative samples, right. Number of negative samples we have already discussed, Tn plus Fp, right. How many of them are wrongly predicted to belong to the positive class? Fp. So, this Fp number of instances have been predicted as positive, but that is wrong. So, Fp by Fp plus Tn, this is called false positive rate. So, you see here false positive rate is 1 minus true negative rate, is not it? Okay, you can easily see this. Now, let us take an example. Say this is your network, okay, and the yellow lines are actual edges and dotted lines are edges which are predicted, okay. So, how many actual edges are there? Actual edges are AB, BC and CD, right. So, these are positive samples, actual positive samples. How many actual negative samples are there? So, those pairs which are not connected, AD, BD, AD, BD and AC, these are negative samples. Now, let us look at the prediction. Our prediction says that the positive links are these dotted lines AB, BD and BC. These are predicted positive links, and predicted negative links are BC, AD and AC. Sorry, DC, not BC, DC, DC, AC and AD. Okay. So what is true positive? If you look at here carefully, true positive is, so let us compare these two sets, okay. So, true positive would be which one? AB, AB, AB and BC, BC. So, true positive is 2. How many of them are false positive? Only one, this one. How many of them are true negative? Let us compare these two sets, right. AD, AD, AC, AC, right. 2. So, 2 of them are true negative, and how many of them are false negative? 1. So, we got the confusion matrix now. So, the accuracy would be this plus true negative this by total. Precision would be true positive by true positive plus false positive 0.67. Recall would be true positive by true positive plus false negative 0.67. True negative rate you can measure, and false positive rate also you can measure. Okay. So, now let us try to understand why accuracy is not a not a good measure. So, what is accuracy? Accuracy says true positive plus true negative by all, right. Now, let us think of an imbalance classification problem, because link prediction is ultimately an imbalance classification problem, right. So, you have 9 actual negative edges and 1 actual positive edges in the ground truth. So, if you blindly say that look, all the pairs are negative edges, all the pairs are negative, right. Your algorithm says that all the pairs are negative. There are 10 pairs and all the pairs are negative, right. So, then what would be the accuracy? So, there are 9 negative edge and 1 positive edge, and your method says that all of them are negative. So how many true negative cases are there? There are 9 true negative cases, because your method says all 10s are negative, but out of them 9 are actually negative. So true negative is 9, okay, but true positive is 0, okay, and total is 10. So the accuracy is 9 by 10, 0.9, 90%. Think about it. You can blindly say that everything is negative and still you get 90% accuracy, right? You are unable to predict the the smaller class, right? You are unable to predict it, but you still got 90% accuracy. That's the problem of the accuracy measure, okay? So how do we get rid of this problem? There are many ways. For example, you can do class wise precision, say precision for positive class, precision for negative class, right? Recall, class wise recall, and so on and so forth. And your target would be to look at the rare class, which is in our case this is a positive class, okay? We look at the rare class, and with respect to the rare class you need to predict you need to measure the precision and recall. But there are even more sophisticated measures, right? So this measure is often used in information retrieval, even in classification as well. This is called AUC ROC. So ROC, the full form of ROC is receiver operating characteristic curve. Receiver operating characteristic curve. Why is the name? I don't know, okay? And area, and then what we will do in this, so we plot this ROC curve and we look at the area under this ROC curve, okay, and the area would give you the measurement, the accuracy. Now let me discuss what is this AUC ROC metric, okay. So let me let's take an example. So let's say link prediction problem again, and you have different pairs, say AB, BC, right, CD, okay, and you know their labels, actual labels. So this is 1, 0, 0, whatever, right, and you also know their predictions. So this is actual, right, and your prediction, right, your prediction is say 1, 1, 0, something like this, okay. So whenever you predict, whenever you run any classifier, the classifier also outputs a probability, right, a confidence that okay, the model says that with probability 0.9, the model says that this is a positive instance. With probability say 0.8, you say that this is a negative instance, and so on and so forth. So we will discuss later in some link prediction algorithms that these probabilities are also returned, okay. So given this thing, how do we draw the AUC ROC curve, okay. So what you do first, we first rearrange all those instances, sort all the instances based on this probability, right. Say AB will come first, its probability is 0.9, then say CD would 0.87, right, EF 0.8, and so on and so forth. We sort it based on the probability obtained from the classifier, okay. And then what you do, and we also know their actual labels, right, say the actual label is 0, 1, 1, and so on and so forth, okay. Now let us assume that this sample is T1, or say whatever T1, this is T2, this is T3, and so on, okay. So let us only look at T1. So this is T1 and confidence is 0.9. So I will assign all the instances as positive whose confidence value, whose corresponding confidence value is greater than equals to 0.9, right. So I will say that okay, this is positive because my threshold is 0.9, So whatever comes above 0.9, on and above 0.9, everything will be classified assigned as 1. So this is 1, all the others are 0. So with respect to the first instance T1, we get a prediction. So with respect to the confidence level of the first instance T1, we get a prediction of all the other instances, right? And we can, if we get this, we can draw this confusion matrix, right? Because we know the actual levels, we will get and we can measure true positive rate and false positive rate, right? Remember the AUC ROC curve you see here in the previous is basically a curve where x axis is the false positive rate. False positive rate is something that we discussed already, right? False positive rate, right? And y axis is true positive rate. What is true positive rate? True positive rate is same as recall, right? It is basically true positive by true positive plus false negative. Okay, this is also called sensitivity. And what is false positive rate? We have already seen false positive rate is 1 minus true negative rate, and true negative rate is called specificity. So false positive rate is 1 minus specificity. Okay, so we basically draw a curve between a curve where x-axis is 1 minus specificity and y-axis is sensitivity. These are just names. Okay, recall, y-axis and x-axis is false positive rate. Now, for the first instance, you can measure true positive rate and false positive rate. You get some value. Let's say you get some value. Okay. Now you take T2, this one, and you know that the same thing. So the threshold is 0.87. So on and above the threshold, everything would be 1, others would be 0. So true positive rate and false positive rate you can measure. T3 similarly you can measure. Okay. So these are all pairs and you have false positive rate and true positive rate. You can plot it, right? Let us say the plot looks like this, and remember this always ranges between 0 to 1. This also ranges between 0 to 1. Okay. So if you look at this square, the square, the total area is 1. Okay. So for a particular model, so this is for a particular model M1, you will get a curve like this. Now think about the curve, right? This will never decrease. Why this will never decrease? With the increase of false positive rate, right? You keep adding false positives. If you keep adding false positives, right? Let us again go back, you will understand. Okay? Go back to the formula. You keep adding false positives, your recall will never change, right? So with the increase of false positive, say for example, you have drawn this curve and you are planning to draw the remaining shape of the curve. You are at this moment, this position. You have certain false positive value, right? This is a false positive. You increase false positive, right? The false positive will increase, but this will never decrease. This will either remain same or increase. Okay? Recall will never decrease. Because what is recall? Whatever you have, whatever positive samples you have returned so far, divided by out of all the positive samples. Okay? So the curve will never go down. Okay? This will motorically increase. And what's the best possibility? Now say for M1, for a model M1 you get this curve. For model M2, say you get another curve like this. So this is ROC curve, okay, and AUC is the area under this ROC curve. So for M1, I actually measure this area. and we know how to measure this area. For M2 we measure this area, and the idea is that higher this area, better the model. Why? Think about it. What would be the best case? With little false positive, if I get the maximum true positive, right? Say I get a, so with this false positive I get a true positive like this. That is the best case. Okay. So the more the curve actually move towards this boundary, better would be the model. So this is AUC ROC, and this is important particularly in case of imbalance classification problem. Okay. So let us look at the last metric that we use. This is called precision recall curve. Now precision recall curve gives you the flexibility to choose a particular recall value and identify the corresponding precision, right? Sometimes what happens is that you are told that, look, I want to understand the precision value at recall 0.3. I want to understand the precision value at recall 0.4, right? So this curve gives you the entire spectrum of it, right? So what is this curve? X axis is the recall and y axis is the precision. Okay. So you return an item, right? You return an item and you predict it whether it's positive or negative. So let's say you have these items, right? Item 1, 2, 3, 4. In our case, items are pairs of nodes, and you predict it as 1, 0, 1, 0, and so on. So till this part, you have a precision recall value because you already know the actual value, actual label of this. Say this is 0. Till this part, you know the precision recall. Till this part, you have a precision recall. This part, precision recall, and so on and so forth. Right? So as you increase your recall, so eventually you will return all the positive samples. So eventually your recall will be 1, right? But precision will decrease significantly. So this is precision recall curve. You can say that, okay, at 0.4 I know the precision, 0.6 I know the precision. Similarly with 0.7 precision, right? 0.7 precision I know the recall. Okay. So that is about the evaluation matrix. The unique problems of link prediction we have already discussed. The first problem is that it's very difficult to collect temporal information, right? So this temporal change is hard to collect. Oftentimes we look at a mixture of addition and deletion, but we generally look at, when we talk about link prediction, we only focus on addition of edges. We do not consider deletion of edges. That is also a problem. We generally do not explicitly consider the sign of an edge, whether it is a positive or negative. We do not consider the weight of an edge, the direction of an edge, right? Link direction prediction problem again is a separate problem, separate problem statement, right? And of course, the class imbalance problem itself is a major major setback here. Okay. So we stop here. The remaining part of this chapter we will discuss more of an algorithms for link prediction. Okay. Thank you.